1, 0.
1, 2, 3, 4.
Hi everyone, welcome to part 1 of solving trig equations. We're going to split the lesson into doing most of these questions today without a calculator. The very last example uses a calculator, and then next class we get into some questions that will involve a little bit more of the calculator, some quadratic formula, and will just be a little bit more challenging. So here's part 1. So we could go through each of the steps right now, but instead of doing that, let's jump into a question, and through the question, let's see what we could do to show how the steps work. So if we're saying solve 2 sine x minus 1 equals 0, sine x is representing a variable. And if sine x is representing a variable, then you just want to isolate your variable. Let's get it on its own. So let's add 1 to the other side. And then let's divide both sides by 2. So we could say sine x is equal to 1/2. And they want to know, when is x true for sine x being equal to 1/2 between 0 and 2 pi? And then after, you're going to keep seeing this, can you express it in general form? And so we know from past lessons, when sine x equals 1/2, you would start by drawing your quadrants. And we can write in here our cast. Sine x is equal to positive 1/2, and sine is positive in quadrant 1 and quadrant 2, so we can construct a triangle in quadrant 1, construct a triangle in quadrant 2, and from your reference angle, you can apply your SOHCAHTOA, your opposite over hypotenuse for sine. So 1 and 2, and 1 and 2. Each of these questions here are going to create something to do with either a quadrantal angle triangle or a special angle triangle. So we know here we have our 1√3:2 ratio. And if we're talking in radians, then from our reference right here, going opposite to that 1, that's going to be a pi over 6. We know it's 30 degrees, part of our 30, 60, 90 triangle, but it's a pi over 6 in radians. So we'll say this is equal to pi over 6, and that's going to be one of our terminal arm solutions. And then our second solution we'll find by saying I'll travel over the entire pi, but then I'm going to backtrack that pi over 6, and 1 full pi subtract a 1/6 of a pi will leave me with 5/6 of a pi. So that's going to be my second answer right there. If you're still thinking in degrees, you're welcome to do so. Just make sure that you convert it to radians at the very end. So in terms of our solutions, pi over 6 and 5 pi over 6 are the two solutions that satisfy this from 0 to 2 pi. And if they want to know what that would look like in general form, sine x has a period of 2 pi, meaning that going around this circle is going to take a full distance of 2 pi. So these solutions are going to continue on whenever we have a pi over 6 plus every multiple of 2 pi. And then we'll say where n is representing any integer. And we'll use the capital I there, knowing that if you used a Z, that's probably something a little bit more proper, and that would be the international symbol for an integer. Okay, so part marks for being able to say what are the solutions from 0 to 2 pi, and then also making sure you include the general form. Let's take a look at the steps now, and let's see what we did just to confirm that we followed the step-by-step process. We isolated our variable. Then we applied our cast, we wrote out our cast, and we said we're in quadrant 1 and 2. We constructed our special angle triangles. We saw that we had a 30, 60, 90 triangle, and we found our solutions from 0 to 2 pi. Hey, each of these questions have a little bit of an additional twist. If you look at example 2 right here, we want to be able to isolate for our variable. Our variables are on each side, so we want to be able to join like terms. Let's add cos x onto this left side right here. And if we do that, we get 2 cos x. 1 cos x plus another cos x is 2 cos x's. And then we want to subtract the root 2 onto the opposite side. Whoops. And now we want to isolate for cosec, so we'll divide, oh, sorry, my fault. We'll divide by 2, and we'll divide by 2. And cosec equals negative root 2 over 2. Now this may look familiar or it may not look familiar. So depending on how you see this, we just need to know that saying root 2 over 2 is equivalent to saying 1 over root 2, and in this case we're talking about some negatives. That's because what we've done is if you had root 2 over 2, all that is rationalizing the denominator to be able to go here. If I times this side here by root 2 and this by root 2, we would go back to our original form. So we need to know those are equivalent to each other, because most of the time we deal with something that says 1 over root 2 rather than root 2 over 2. Regardless, from here we can go on to creating our cast, and we know that cosine is negative, and in this case cosine is going to be negative in quadrant 2 and quadrant 3, so we can construct our triangles here. And using our ka from our reference angle, we know that it would be adjacent over hypotenuse, adjacent over hypotenuse. And we've created a 1:1 root 2 ratio, which reminds us of our 45, 45, 90 triangle for our special angle triangles. Thinking about something like this, if we want to be able to figure out exactly what it is, we know that going all the way around to here would be a full pi, pi being halfway right here, subtract the pi over 4, that 45 degrees converted to radians. So pi, subtract a quarter of a pi, would leave us with 3 pi over 4 as one of our solutions. Then to find our second solution right here, we would have gone the full halfway plus an additional pi over 4. So you'd have pi plus pi over 4. So 1 full pi plus a quarter of a pi. If you get a common denominator, eventually that's going to add to 5 pi over 4. So these are our two solutions between 0 and 2 pi. Again, if you're feeling more comfortable in degrees, you could say, hey, that was 180 minus 45, which is 135 degrees, and you could convert the 135 degrees to 3 pi over 4. Likewise, you could have said 180 degrees plus 45 degrees is 225 degrees, and that converts to 5 pi over 4. Feel free to do that, but it's nice to be able to start to think in radians first and foremost. For our general solution, again, cosine has a period of 2 pi, so we can say we're going to have solutions for this at 3 pi over 4 plus every 2n pi, and at 5 pi over 4 plus every 2n pi, where n is any integer. Okay, now you were seeing that these are a little bit more routine. So what I would recommend for example 3 is, now that you've seen these first two, I would pause it, give this one a try on your own, and see if it matches up with the end solution. Let's isolate our tan x, so subtract 1 to both sides. We have root 3 tan x equals negative 1. Divide both sides by, divide both sides by root 3. Tan x equals negative 1 over root 3, and we can construct our cast. Tan is negative, and tan is negative in quadrant 2 and quadrant 4. So from there we can construct a triangle in quadrant 2, triangle in quadrant 4. Tan is opposite over adjacent, so 1 and root 3. In quadrant 4, here's opposite and adjacent. Notice I didn't put in the plus or minus signs. I didn't do that for the previous example either, and we don't have to, because we know where we are. We're in quadrant 2 and quadrant 4, but technically I guess we should say that's a negative and that's a negative. To identify what our terminal arms are here and here, we know that we have a 1 root 3 2 ratio, which gives us one of our 30, 60, 90 ratios, where our reference angle is 30 degrees, or as we'll say, pi over 6. So then to travel all the way over here, it's the full pi, take away a 6 of a pi. So we're going to have 5 pi over 6 is one of our solutions. And then we're going to go over the full 2 pi, take away a 6 of a pi, and we're going to get 11 pi over 6. So those are our two solutions between 0 and 2 pi. And to express this in general form, we could say one of two things. Tan, remember, is unique, as opposed to sine and cosine, which have periods of 2 pi when there's no b value changing anything. Tan has a period of pi. And if you think about what happens when you add pi from 5 pi over 6 to get 11 pi over 6, we added a single pi. And that's going to happen again and again and again because they are directly opposite to each other when you move around this circle. They're halfway to each other. And so what you could do is, for a general solution, you could actually come up with a really clean answer and say it's just x equals 5 pi over 6 plus every n pi. And that would satisfy absolutely everything, because if you add 1 pi to that, you would be at 11 pi over 6. And as you continue to add 2 pi's and 3 pi's and 4 pi's and so on, you're going to get each individual solution. So you don't have to have two separate statements for your general solution. You can just say that one statement and everything will be okay. Now, if you had written it out separately as two separate things and you said something like, well, would I get marks off if I also wrote x equals 11 pi over 6 plus every n pi? That's also correct. We would mark that correct. It's just a little redundant, so we don't need to have that there. So if the first three examples were fairly similar to each other, now we get something with a bit of a twist because we have a sine x and we have a tan x. In other words, we have two different types of variables in the same equation. Trying to think about how we would go about solving for something like this, we want to get everything onto one side and see what that would look like. Sine x tan x minus 2 tan x equals 0. Probably the most common error for a question like this would be to look at that and say, well, can't I, instead of bringing everything onto one side, couldn't I have just divided both sides by a tan x? And we'll show you quickly why that's not the case. If you have something like this and you were to proceed from here and you have something on the left side where you have a greatest common factor, they each share tan x, you could factor out tan x and then you'd be left with sine x minus 2 equals 0. And what that tells us is one of two things. It tells us that tan x is equal to 0 and that sine x is equal to 2. If we had divided by tan x initially in our first step and essentially eliminated the tan x, then we would have never had that potential solution of tan x being able to equal 0, and we wouldn't have been able to give our full answer. So just remember, when you see a question like this, you want to be able to bring everything onto one side, and you want to look for factors, and you don't divide by the tan x. So this is something that's really important to be able to remember when you see multiple variables. Let's deal with sine x equals 2 first, and that may look unfamiliar because if you think about it, it's really saying 2 over 1. And if you're thinking of sine x and sine being opposite over hypotenuse, it's essentially saying this would create a ratio in which your opposite in your triangle is 2 and your hypotenuse is 1. In other words, your opposite is greater than your hypotenuse, and that's an impossible situation. So because of something like that, if you entered the inverse of sine x into your calculator and you want to solve for it and you said equals 2, it's going to come up as saying error. This is not something that we can do. So from here, there's actually no solution. Another way of thinking about it is think about trig 1 when we graphed sine x so many times. If you graphed sine x here and you had a maximum of 1 and a minimum of -1, and then it was set equal to 2, you would have something here where they would never ever intersect with each other because you would never have something above 1. So there clearly can't be an answer for sine x equaling 2, or in this case for sine x equaling anything greater than 1 or less than -1. So for tan x equaling 0, there's a couple ways we could go about this. If you want, you could draw your quadrantal angles, because whenever tan x is equal to a 0, it's going to resemble something with a quadrantal angle. And so just recall what that means. Remember, tan is equal to the ratio of y over x. And what you want to be able to see is if you divide the y by the x, what would produce a 0 value? And it occurs right here at the beginning where you would have 0 over 1, your y value divided by your x value. And would also occur right here where you'd have 0 divided by 1. And so because of that, you would get a solution at 0 and at pi. I think that may be our best method of doing it. Some people may also like to do a mini graph if you feel like you've graphed tan a lot in the past, which probably isn't the case. But if you feel like you're confident in terms of what tan would look like on a grid, then you could always just say, well, I know that tan looks like this, where I would cross at 0 and pi. And if you feel like you could do that mini sketch pretty quickly, then feel free to use that instead of being able to draw the unit circle. Regardless, you get solutions of 0 and pi. To be able to answer the general form, once again, because we're looking at tan solutions, if you were to continue on and you're to look here, our next solution would be at 2 pi, and then 3 pi, and then 4 pi, and so on. So our general solution is just going to be x equals every n pi, where n is an integer. Okay, so now we've expanded, and I bet you would say if I look at secant squared x minus secant x minus 2 equals 0, it should look like something where it's some sort of something that may be factorable as a trinomial. Think of all the trinomials you factored in the past few years where you see something in this form with an x squared value and an x value and then a constant. So if you have something like this, let's see if we can factor the trinomial. We'd be saying, what are two numbers that multiply to -2 and add to -1? And in front, we'll have a secant x and a secant x, and two numbers that times to -2 and add to -1 would be -2 and +1, meaning we would get a solution of secant x equaling 2 and secant x equaling -1. Now, based off of this, we can either think in secants or you could think in cosines and try to convert it. Either or is going to be okay in this case. So let's take a look at secant x equaling -1 first. If you think about something like that, you could do something where let's try a mini graph, and if you were to sketch what cosine looks like, here's 1, here's -1, and in cosine right here at pi, you would have something at -1, and you know that when you take the reciprocal of -1, it would produce its invariant point, because the reciprocal of -1 remains -1, meaning that one of your solutions is going to just be pi. If you're saying, I didn't follow that, I don't like these mini graphs, you could also look at it around a unit circle right here. So we have 0, pi, pi over 2, and 3 pi over 2. So if we label our points here, we got 1, 0, 0, 1, -1, 0, and 0, -1. Okay, so the question is saying, when is secant x equal to -1? So think about what secant x would be equivalent to. We know that cosine is the x value. And let's find out when the x value is at, if we want to see where the x value is at -1. And it's only time it is between 0 and 2 pi is right here. And so because of that, we know that that's one of our invariant points, and so it'll be right at pi. For secant x equaling 2, we can think of this in two ways. Well, let's keep it as secant x, and let's write it as 2 over 1, and let's draw our cast. Cosine is positive in quadrants 1 and quadrant 4, so secant x will also be positive in quadrants 1 and 4. And we can create a ratio here and here. And if cosine is ka, then secant would be ha, hypotenuse over adjacent. So our hypotenuse will be 2 and our adjacent is 1. And we've created another 1 root 3 2 special angle triangle. This time our reference angle here that's going to be a 60 degree, or in radians we're talking about pi over 3s. And so the distance that we go to be able to cover that would be at pi over 3 for quadrant 1. And then for quadrant 4, we've gone over the entire 2 pi, take away 1/3 of a pi, which is our reference angle, and 2 pi, take away 1/3 of a pi, is going to leave us with 5 pi over 3. And so that would be our other solution right there. Now, if you wanted to, you could change these secants into cosines right away. So imagine you're starting the question from scratch, not from scratch, but where you had secant x equaling -1 and secant x equaling 2. You could take their reciprocals and you could say, when is cosine x equal to -1 and when is cosine x equal to 1/2? And if you chose to do that and solve for when cosine x is -1 and when cosine x equals 1/2, then you'll get a solution just as good there. So if you're saying I don't feel very confident dealing with secants, you can always just switch them once you find your ratios into cosines. Finally, we have to answer what our general form is, and we have a pi over 3, and a 5 pi over 3. So based off of that, we would have to say something along the lines of x equals, it occurs at pi over 3 plus every 2n pi, 5 pi over 3 plus every 2n pi, and pi plus every 2n pi. Okay. And that's our general solution for something like that. Okay, so let's continue on and let's see what we could do for something with example 6. If you have cosecant squared x and a sine x, can you think of a way in which you'd be able to say this in a way that has just one variable rather than two variables? Think back to your Pythagorean identities where you have sine squared x plus cos squared x equals 1, meaning that cos squared x is equal to 1 minus sine squared x. So you could rewrite this and you could say we have 2, and instead of writing cos squared x, you could write 1 minus sine squared x plus 3 sine x minus 3 equals 0. And then we can distribute here and we can try and clean this up, and you get 2 minus 2 sine squared x plus 3 sine x minus 3 equals 0. And then based off of this, we want to probably bring either factor out a negative or bring everything onto the other side, just so that we can have positive squared values to be able to deal with when we start to factor this. So I'm going to join this 2 and this -3 just to say we have a -1, and then I'm going to bring everything onto the opposite side. Let's say here we have, let's add 2 sine squared x onto the right side. And let's subtract 3 sine x onto the right side, and then let's add 1. And so if you have something like that, then once again you have a trinomial that you should be able to factor with this. And here, depending on the way you factor trinomials with the leading coefficient, we could say something along the lines of, it's going to end up being, let's check that out. 2 sine squared x minus 2 sine x minus sine x plus 1. That works. Okay, so we get something here where we would come up with sine x equals 1 and sine x equals 1/2. So whenever sine is equal to 1, 0, or -1, then we're going to have an example of having a quadrantal angle. That's true for sine and for cosine. And so for our quadrantal angles, we could, once again, we could draw our unit circle, and you want to find out when do you have something in which your y value, which is the sine value, is equal to 1. And the y value is equal to 1 at pi over 2, right at the top right there. So one of your solutions here is going to be pi over 2. And then for when sine x equals 1/2, you could draw your cast. And you know that sine is opposite over hypotenuse, positive in quadrant 1 and quadrant 2. And that's going to give you a pi over 6 and a 5 pi over 6 solution. And then once again, you can write your general form. You could say x equals pi over 6 plus every 2n pi, 5 pi over 6 plus every 2n pi, and pi over 2 plus every 2n pi. And you might be saying, well, is it always going to be 2n pi for sines and cosines? It's true unless there's going to be some sort of b value that's going to adjust that. So we'll get that into part 2. So for next day's lesson, you'll see some exceptions where it might not be quite as straightforward as that. But for now, yes, that's as straightforward as it gets. Okay. So this question can be confusing because it's one of those things where if you can't get by step 1, it might be tough to figure out what to do. We have a single cos x and a single sine x, and we know that we can't change anything with our Pythagorean identity for anything like that, because sine squared x, let's say this, cos squared x plus sine squared x equals 1. A common misconception is people think then that maybe cos x plus sine x equals 1 or something like that, and that's not true at all. So don't get stuck into that. So what we could say, if we have a cos x and a sine x, and we can't really make them the same right away, and you're trying to think of, well, what could we do to try to create them so that there is only one variable? You could play around with things, and what I would recommend is let's try squaring both sides. If we square both sides, we would now have a FOIL on the left side. And then on the right side, we would have sine squared x. And if you expand the left side, that looks pretty good. And if we're trying to think of some things that we could potentially do to clean this up, we now have something in which we have sine squared x's and cos squared x's, which means we now can call upon our Pythagorean identity. And so if you think about one of our Pythagorean identities where we say cos squared x plus sine squared x equals 1, and we isolate for sine squared x, we could use this, because now if we replace sine squared x and write it in terms of cosines, instead of having 2 variables, you would only have 1 variable. And so what I mean by that is we can rewrite this, and then instead of saying sine squared x, we could say it's 1 minus cos squared x. We could bring everything onto the left side. So we could add a cos squared x and add a cos squared x and subtract 1. And then based off of that, we get 2 cos squared x plus 2 cos x equals 0. We factor out a 2 cos x, and we're left with cos x plus 1. So from here, we could say cos x equals 0 and cos x equals -1. like what we talked about in the previous question, whenever you have a 1, a 0, or a -1 for cosine or sine, these are examples of our quadrantal angles. And so from there, if you want to do a mini graph, you can do a mini graph. If you want to draw your quadrants, you could draw your quadrants, and you would find that cosine, which is equivalent to your x value, is going to be 0 at pi over 2 and 3 pi over 2. And cosine is going to equal -1. We have -1 right here, and that's at pi, right at -1, 0. And so because of that, you get another solution at pi. And so our three solutions are pi, pi over 2, and 3 pi over 2. And once again, we could write that in general form, and we could say x equals pi over 2 plus 2n pi, pi plus 2n pi, 3 pi over 2 plus 2n pi, NEI. Now, if you wanted to clean something up, you could potentially try to compress that into two statements. You could join pi over 2 and 3 pi over 2 and say, could I have just written pi over 2 plus every n pi, and then I don't need to write this last statement? And if you can see that, then that's absolutely true. But I think for simplicity, we don't need to say that. And you could say 3 pi over 2 plus 2n pi. So both solutions are equally acceptable, and you might even come up with something else from there to try and make it a unique way of saying your general solution. But that's how we go with those questions. Okay, finally, we have a decimal question. So you have to have a calculator for a question like this, and they're saying, well, what would be the solutions for something like cos x equaling -0.4821? Well, let's look at this by two ways. Let's first look at it by saying, if I was to solve for this and I was to graph my solutions, I know that I would have a solution where cosine is negative in quadrant 2 and quadrant 3. So there's going to be two solutions between 0 and 2 pi. And in order to find out what those solutions are, we really need to know what the reference angle is. And so if you take your calculator and you think about, make sure you're in radian mode, and you say, well, what would happen if I did second cosine of, well, I could put in -0.4821, and if I did something like that, it would be okay. The problem is I would get something in which I would find my solution for quadrant 2, but it wouldn't tell me necessarily what my reference angle is. And so when you see a negative angle for negative ratio for one of these, I would say let's ignore the negative, and we want to do that because that way we can find the reference angle. So let's find the reference angle first, and I think that's going to make everything a whole lot easier. And so going back here, we'll say it's 0.4821. So we didn't put the negative in there. And we get something along the lines of, let's say 1.07. I'm not sure if it said what to round it to. We'll say 1.07. And so if we get 1.07 being our reference angle, then from here, we should be able to say, well, that means that this is 1.07, this is 1.07. We can leave the exact value in our calculator, and we know to find out how far terminal arms traveled, it would have been a full pi, take away the 1.07, and then a full pi plus the 1.07. And you can even go back to your calculator here, and you could say, okay, so let's go. There is my reference angle, and I'm going to say it's that plus pi, and I get 4.21 is one of my solutions. And then similarly, I could have said pi subtract, And let's go with the 1.0677. Put in a few more decimal places, but I think they'll do the job. And we get 2.07. So 4.21 and 2.07. 4.21 and 2.07. These would be each of your individual solutions. And then if they wanted to find our general solution, we could always say that means that x equals 2.07 plus every 2n pi, or 4.21 plus every 2n pi, where n is an integer, and that would be our general solution. And as a final way of being able to look at this, let's try something like this. Let's go to our graphing calculator and let's put in for y1 cos x and for y2 this negative 0.4821. Okay, so take a look back here. Let's go to y equals, clear what you have in there, and let's put in cosine of x, and then let's put in negative 0.4821. And let's go to our window. Let's make our x min 0 and our x max 2 pi, because we want to see what's happening from 0 to 2 pi initially. Let's not worry about our scale. 90 is a little bit strange, but that's probably because it was in degree mode from before. So we can put in pi or something like that. And let's put in here maybe negative 2 to 2 for y min, y max. So if we graph this and we want to see these two intersects from 0 to 2 pi, I bet that you can predict what's going to happen. We can press enter 3 times. We get 2.07. Second trace intersect. And we go over here. Press enter 3 times, and we get 4.21. Probably an easier way than method 1, just putting it straight into the graphing calculator, and you can see what happens right away. And just for one more thing, just so you can see what the general solution is, let's say if instead of having 2 pi here, let's say we had something like 10 pi. If you graph this, you can see now how by adding every 2 pi increments, you're going to continue to get the exact same solutions as you go along, and that's the whole essence of being able to create these general solutions. It'll go on forever by adding 2 pi. Okay, so we'll pause right there. Right now, in terms of homework, just make sure you ask in class what we've been able to assign up to, and the next class we'll take a look at part 2. But that's part 1 of trig equations. Thanks.